Hi, and welcome to D.1 Gravitational Fields. It's a whole new theme, the theme of fields. And you can see it's quite late at night here, which is just proof that I work my socks off for you guys. I want to make sure you're going to get great grades and amazing confidence in IB physics, and this is the place to get it.
Let's start this topic with a nice, easy learning objective. State Kepler's 3 laws of motion. Kepler's first law is often called the law of ellipses, and it's based around the fact that the Sun is at the centre of the solar system and the planets orbit the Sun with an elliptical motion or an elliptical curve. His first law takes that a little bit further and says planets orbit the Sun in a path described as an ellipse, with the centre of the Sun being located at one focus. So we have 2 focuses when it comes to an ellipse, focus 1 and focus 2. You'll always find the Sun at one of those 2 focuses. When you look at the distance from the focus to the planet, and let's call that x1, and then from the other focus to the planet, and you add them together, let's just give that a number, let's say it's z. And then you take the planet a time later, time 2 later, and you add the distance from focus 1 to the planet and focus 2 to the planet. The sum is always the same. And that's what this sentence here means. An ellipse is a special curve where the sum of the distances from any point on the curve to 2 fixed points is constant. And that's what Kepler's first law, the law of ellipses, is all about. I'd like to look at an ellipse a little bit further. You can see here on the elliptical diagram that we have F1 where the Sun is and the other focus F2. I'd like to think, what happens if we push these focus a little bit further together? What would happen to the shape of the ellipse? Well, I'll just draw it up here. If we pushed them a little bit closer together, the ellipse wouldn't quite be as spread out and flat. It'd start to get a bit fatter, wouldn't it? And in fact, if we got even closer, we get fatter still. And if we brought them to the one point, that shape would become a circle. So the special case of an ellipse is when the 2 foci are moved together to a single point, and that's called a circle. Now, the maths of an ellipse is very tricky, and it makes physics very difficult for us. So what do we do as physicists? Let's just assume the planet's ellipse is a circle. We talked about this earlier in the course. Sometimes we make assumptions in physics to make calculations easier. And this is one of the assumptions. One of the assumptions is that a planet's ellipse is a circle. It just makes everything easier. But Kepler wasn't fully ready to adopt the circle assumption just yet, because first he came up with his second law, the law of equal areas. I want you to look at this diagram, and this diagram has our 2 foci here, and we have a planet going round in an ellipse. This section here is how far it travels in 1 month around the ellipse. This section here, relating to area 2, is how far the same planet travels at another month throughout its orbit. And you can see it travels a smaller distance around the ellipse in the second month than it does in the first month. So what's Kepler got to do with this? Well, his second law is the law of equal areas, and he says a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. So in 1 month, this area is swept out by the planet, and in another month, this area is swept out by the planet at a different point in the ellipse, but both areas are the same. How can that be? Let's think about it in terms of energy. I want you to think about the planet. I'm going to draw the planet here. When we're looking at the first month, let's call it month 1. It's really close to the Sun, which means it's going to have a low potential energy. And in month 2, it's going to have a high potential energy because it's far away from the Sun, right? But this is a system where the total energy is constant. What other type of energy does it have? Well, it's moving. So that means if the total energy is constant and it's got kinetic energy, then when it's close to the sun in month 1, it must have a high kinetic energy. And when it's further away from the sun, it must have a low kinetic energy to keep that total energy constant. That means it's moving faster here and it's moving slower there. So this law, what it really does is it relates to the speed of the planet in the orbit. It says, okay, if these areas are equal, then it must be moving faster when it's closer to the sun and slower when it's moving further away. Finally, Kepler's third law, and we're going to look at this law later because this law is often asked to be proved. Kepler's third law is the law of harmonies, and he said that the square of the orbital period of the planet, t squared, is directly proportional to the cube of the radius, r cubed, of its orbit. Let's draw a little diagram. We've got a star with a planet orbiting it. The radius is here. And the time period is the time taken to go all the way around and back again. Time period. And what that's saying is that the time period squared is proportional to the radius cubed. And that radius is to the centre of the sun, by the way, and the centre of the planet. And when we have that directly proportionate relationship, we can, of course, plot this graph, which is t squared on the y-axis and r cubed on the x-axis. And the equation of the line is y equals mx because there's no intercept. So t squared, which is on the y-axis, equals m r cubed, which is on the x-axis. And this m value is the gradient, right? So the gradient is m, and we're going to look at that value later, and we can get loads of interesting stuff from that value later.
I'd like now to talk about Newton's law of gravitation. The difficulty with this law can be purely mathematical, and that is simple maths. It's forgetting to square the r, or it's not typing things into your calculator properly. Let's have a look. I'd like you to consider the Earth and the Moon. We know that the Moon orbits the Earth, and that the Earth exerts a gravitational force on the Moon, and the Moon exerts a gravitational force on the Earth. This gravitational force acts at a distance and has an associated force field, much like a positive or a negative charge or a magnet. Because of Newton's third law, when we say that the Earth exerts a gravitational force on the Moon, there must be an equal and opposite force. So the Moon exerts an equal and opposite gravitational force on the Earth. Of all the forces in the universe, gravity is the weakest, and it's only measurable with large masses. So we can only really measure gravity when we're looking at planets. Although, if I was to stand next to my best friend, I would be exerting a gravitational force on her, and she would be exerting a gravitational force on me. I have the ability to create a gravitational force, I'm just not massive enough. Let's look at this force in more detail. This gravitational force that the Earth exerts on the Moon and the Moon exerts on the Earth is directly proportional to the product of the masses. So the bigger each of those planets are, the bigger the force is. It's also indirectly proportional to the square of the distance between the masses. So if these planets were to get closer to each other, if this planet and the Moon were to get closer to each other, the force would increase with a squared factor. This idea of maths, this relationship that we're building here, is built on one assumption. It's built on the assumption that the masses, or the Earth and the Moon, have uniform density and that the mass is concentrated at the centre. So all this mass within the Earth, we have to pretend it all comes from a central point, a point mass in the centre. Let's take this mathematical idea a little bit further. We previously said that the size of the gravitational force is proportional to the product of the masses. So force is proportional to the product of the masses. We also said it was indirectly proportional to the square of the distance. This formula has built upon these two assumptions, and to make it into a reasonable relationship rather than a proportionality, we've introduced a constant of proportionality. Well, not us, Newton. Newton introduced the constant of proportionality, and his constant of proportionality is G, big G, not a small g, big G, which is 6.67 times 10 to the minus 11 newtons metre squared per kilogram squared. This is given in your data booklet. You will be asked to find the gravitational force between two objects, and you will have to use this formula. Please, please, please remember to square your distance. That's where a lot of people make silly mistakes. Time for some more actual examiner feedback. The examiners have said that candidates could not provide a statement to encompass Newton's law of gravitation.
So what does that mean? That means that perhaps in a past paper or an exam paper, you've been asked to describe Newton's law of gravitation. And it would be not suitable to simply write down this equation. You would have to come up with a statement to describe Newton's law of gravitation. And that's where we go back to this point here. You would say, Newton's law of gravitation says that the size of gravitational force is directly proportional to the product of masses and indirectly proportional to the square of the distance between the masses. This assumes masses have uniform density and the mass is concentrated at the centre. It's a bit of a mouthful, but certainly something you'd want to memorise. This is probably worth about 3 marks. The most common types of exam question you'd find when you're looking at gravitational force and Newton's law is when objects are in orbit, as we looked at before. In this case, we have a satellite orbiting the Earth. We know from earlier that it's got a centripetal force pulling it towards the centre. But we now know that that centripetal force is gravity. It is the force in Newton's law of gravitation. What that allows us to do is to form a relationship. We can say the gravitational force from Newton's law is equal to the centripetal force. We can put expressions for each of them here. Gmm over r squared for Newton's law of gravitation equals mv squared over r. Both of these m's can cancel out, one of the r's can cancel out, and we can rearrange it to find the velocity of an object at any point, depending on the mass of the central object and the radius of the object that is in orbit. So when we're looking at orbits, always remember that the gravitational force is equal to the centripetal force. And you come out with this easy, very easy expression. However, it can get more complicated. Follow me now. A recent exam paper has delved into Kepler's law, but the paper asked you to prove T is equal to the square root of 4 pi squared r cubed over gm. What? I'd understand it if you totally panicked at that stage. But the clue was they were looking at orbits. And actually, the question is pretty simple. Let's look at these orbits again. We go back to start here. The gravitational force is equal to the centripetal force. Gmm over r squared is equal to mv squared over r. We cancel out the m's. We cancel out one of the r's and rearrange v to equal this. But we also know that the linear velocity is v is equal to 2 pi r over t. So substitute this expression into here, rearrange, and you come out with this very difficult looking formula. This difficult looking formula is a representation of Kepler's third law, gravitational field strength. We are now looking at one object, one large object. Let's pretend it's the Earth or the Sun or some astronomical body. When we're thinking of large masses, a force is felt at a distance all around this large mass. And what that means is there's a field, a force field surrounding this large mass. In order for us to measure anything about that field, we use a test mass. And the reason we use a test mass is because the test mass has a small enough mass that it won't have any gravitational force of its own. That means it won't interrupt or interfere with the measurements made surrounding this large mass. And we define the gravitational field strength as the force per unit mass experienced by a small test mass. Force per unit mass. Force per unit mass. So G, which is a small g for gravitational field strength, is equal to F over m. And you may have come across this in previous studies in physics. Let's take that a little bit further. Gravitational field strength is the force per unit mass experienced by a small test mass. So G is equal to F over m. Gravitational force is equal to Gmm over r squared. So instead of F, let's pop in Gmm over r squared. You can see that the two smaller masses, the mass of the test mass, cancel, and we're left with Gm over r squared. So our expression for gravitational field strength for large masses is Gm, which is the mass of the large mass, over r squared, which is the distance between the centre of the large mass and the point where you're looking for the gravitational field strength. I'd like to look at the field lines in a little bit more detail. If you imagine this as our large mass, you can see that the gravitational field can be shown using a series of field lines. And these field lines are radial, because we're looking at this large mass from a distance. This tells us that the gravitational field strength is a vector because we do care about the direction of this value. You can see that the lines always point towards the large mass, so gravity is always attractive. You find that the lines point towards the centre of the massive object. If you imagine those lines to extend towards each other, they would all combine at the centre of the object. You can see that the lines are perpendicular to the surface of the object, and the lines are closer together near the surface, which means that the gravitational field strength is greater when you're close to the surface. And as we increase the distance from the large mass, you can see that the distance between the gravitational field lines is greater, which means that the gravitational field strength is weaker. And that's why gravitational field strength decreases with distance from an object. There is a sort of special relationship with gravitational field strength. If you're looking at a planet, for example, and we'll say the planet is a spherical mass. Outside the spherical mass, so above the surface of the planet, and this is the surface of the planet here, and you can see this is the distance from the centre of the planet or the centre of the sphere. And what we have here is the magnitude or the size of gravitational field strength. So if we go from the surface of the planet and extend away from it, you can see that the gravitational field strength changes depending on the distance from the planet, and it changes with a 1 over r squared factor. And if you go back to the formula, that makes sense to us. G is equal to Gm over r squared. If the gravitational constant remains the same and the mass of the spherical body or the planet remains the same, then G is indirectly proportional to 1 over r squared. That's what this shows. However, it's a different case when you look inside the planet. So inside the planet, the relationship doesn't hold. Inside the planet, G is, or the gravitational field strength, is directly proportional to R from the centre of the mass or the centre of the planet. So inside, you can see that the gravitational field strength increases in strength in a proportional relationship until the surface of the planet, and at which case it then offers its 1 over r squared. Another special case that you'd like to consider, not quite so much a special case, but something that the examiners are quite keen on, is this idea of two bodies. So the syllabus says that students should be able to determine the resultant gravitational field strength due to two bodies along a straight line. Well, phew, a straight line means it's one-dimensional, which makes our calculations a lot easier. In 2 dimensions, there's all sorts of components that we need to consider, so we can forget about that. But what we do need to understand is that gravitational field strength is a vector, and we have to take into account the gravitational field strengths from one body and the other body, and in the fact that they're acting in different directions. So let's look at this question. A mass at point X gives rise to a gravitational field strength G at point P as shown. So the gravitational field strength felt by the test mass P at this point here from X is G. An identical mass is placed at point Y as shown below. So you can see at point Y there's an identical mass and it's twice the distance away from P. The result is that although P is being attracted to X, it's also being attracted to Y. And the question says, calculate the resultant gravitational field at P. So let's go to my desk cam and solve this problem. The previous slide asked us to find the resultant gravitational field strength at P. And that gravitational field strength is due to two bodies, X and Y, and they're both identical. We know, if we look at body X and say that's a positive direction, we know the gravitational field strength at X is G. Now we look at Y. Y has an identical mass and G will be constant. Big G will be constant. So I'm interested to find out how the gravitational field strength will be affected by the change in distance. So we've got Gm, and instead of r squared, we've actually got 2r squared because it's double the distance than at x. So we can extend that to say Gm over 4r squared. The other thing we need to take into account is the fact that it's in the opposite direction. So we're looking at gravitational field strength being a negative. Therefore, what we have in this direction is we have G, a magnitude of G, felt at P. And in this direction, we have a magnitude of, well, wait a minute. The G's and the M's can cancel out. The R squareds can cancel out. So we have a magnitude of G over 4 minus. So the resultant gravitational field strength is G minus G over 4, which is 3G over 4, or 3/4 G over 4. And that's a plus, because this G is bigger than that G. So our resultant gravitational field strength at P is 3G over 4. I've shown you lots of pictures of a planet and the field lines, and it's called a radial field lines. These field lines are radially outwards, and we've talked a lot about what they look like from afar right now. That's the worst drawing I have seen. Sorry about that, but you get the idea, right? We've got these radial field lines going towards a planet. But what happens when you're on the planet? You don't see it like this, do you? You don't see it from afar. When you're on the planet, I'm sure you'll agree, the Earth looks flat, right? And the field lines are not going to be radial at that stage. So please bear in mind that when you're looking at gravitational field lines on a planet's surface, then the field lines appear to be uniform, or uniform, not uniform. And by uniform, we mean they're all straight, they're all the same distance apart, and they're all at right angles to the surface of the planet. And you can basically assume these field lines to be uniform on the Earth's surface up until about the end of the atmosphere, really. So when we're talking about gravity on Earth, we're talking about a uniform field lines And we're going to use equations like the gravitational force weight is equal to mg. We're not going to use equations like F equals g over r squared. This r squared value is a radial field. So we don't use that when we're looking at gravitation on the Earth's surface. We use the simpler equations that you probably would have learned in middle school or previous GCSE courses.